Imagine looking down at Earth from far out in space. Before we go any further, if you want a brand new Earth topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. From that great distance, our planet looks like a blue marble wrapped in white cloud. Most of what you see is ocean, but tilt your gaze toward the very top of that marble, toward the North Pole, and something changes. The blue gives way to white. A vast, pale circle sits at the crown of the world like a cap of ice and frozen sea. That is the Arctic Ocean. It is the smallest of Earth's 5 oceans. It covers about 5.4 million square miles. To put that in some kind of scale, that is roughly 1.5 times the size of the entire United States. And yet, compared to the Pacific or the Atlantic, the Arctic feels almost hidden. It sits at the top of the world, ringed by land, tucked away beneath a ceiling of ice for much of the year. Most people will never see it. Most creatures on Earth will never come close to it. But it shapes the world for all of them. The Arctic Ocean is almost entirely surrounded by land. Canada, Russia, Norway, Greenland, and Alaska all press in around its edges like hands cupped around a bowl. This makes it the most enclosed ocean on Earth. The Atlantic and Pacific stretch freely across the globe. The Arctic does not. It sits in its own quiet basin, connected to the other oceans only through narrow passages and deep underwater channels. That enclosure gives it a character unlike any other ocean. It is still. It is cold. It is ancient in the way that only truly remote places can feel. The water in the Arctic Ocean is very cold. Near the surface, temperatures often hover just below the freezing point of salt water, which is around 28 degrees Fahrenheit, or about -2 degrees Celsius. Fresh water freezes at 32 degrees Fahrenheit, but salt lowers that threshold slightly. The ocean uses that small difference to stay liquid just beneath the ice, even in the depths of winter, when the surface locks into thick sheets of frozen sea ice. The water below keeps moving, keeps circulating, keeps alive. That ice on the surface is one of the most important features on the entire planet. Sea ice, the frozen layer that forms directly from ocean water, covers most of the Arctic Ocean in winter. its peak, it stretches across roughly 6 million square miles. It reflects sunlight back into space like a giant mirror. Scientists call this the albedo effect, which simply means the measure of how much light a surface bounces back rather than absorbs. Bright white ice reflects about 80% of the sunlight that hits it. Dark open ocean absorbs about 94%. That difference matters enormously for the temperature of the whole planet. The Arctic Ocean sits at the very top of Earth's climate system. It acts like a kind of thermostat, helping to regulate temperatures across the northern hemisphere. Cold air that forms over the Arctic spreads outward, pushing south in winter and pulling back in summer. The ice itself stores cold and releases it slowly. The ocean beneath stores heat and releases it slowly too. Everything moves in long, patient cycles. Nothing in the Arctic happens quickly. That slowness is part of what makes it so powerful. And there is something deeply calming about that scale of time. The Arctic has been cold for millions of years, long before humans built cities or sailed ships. This ocean sat quietly at the top of the world, freezing and thawing with the seasons, feeding currents that circled the globe. It was here before us. It will likely be here long after us. There is a kind of peace in that thought. The Arctic Ocean is also surprisingly deep in places. Its average depth is about 3,400 feet, which is shallower than most other oceans. But in the Eurasian Basin, one of the deep underwater valleys that cuts through the ocean floor, the water drops to over 17,800 feet. That is more than 3 miles straight down. In those dark, cold, crushing depths, life still finds a way. It always does. From space, the Arctic looks still and silent. A white eye at the top of a blue world. But it is anything but still. It breathes with the seasons. It pulses with currents. It holds secrets in its deepest trenches and its oldest ice. And over the next few hours, we are going to explore all of it slowly together, one quiet fact at a time. The Arctic Ocean is the smallest of Earth's 5 oceans. It covers about 5.4 million square miles. That sounds enormous, and it is. But to put it in perspective, the Pacific Ocean is nearly 7 times larger. If you laid the Arctic Ocean flat across the continent of North America, it would cover almost the entire thing from coast to coast, border to border. It is vast by any human measure, but among oceans, it is the quiet, compact one. It sits almost entirely within the Arctic Circle, that invisible line drawn around the top of the globe at roughly 66 degrees north latitude. Nearly every drop of its water lies inside that circle. The North Pole itself sits not on land, but on floating sea ice, drifting slowly above water that is several thousand feet deep. There is no solid ground beneath the top of the world, just ocean and ice and the long silence of deep water. The ocean is roughly circular in shape. It is ringed by land on nearly all sides. Canada, Alaska, Russia, Norway, Greenland, and Iceland all press close to its edges. This makes the Arctic Ocean more like a giant, enclosed sea than an open ocean. The land holds it in. The narrow passages between those land masses are the only places where water moves freely in and out. The widest of these openings connects the Arctic to the Atlantic Ocean between Greenland and Norway. Another, much shallower passage connects it to the Pacific through the Bering Strait, a gap only about 55 miles wide. 55 miles. On a clear day, you can almost see from one side to the other. Now, here is where the story gets ancient. The Arctic Ocean Basin, the great bowl that holds all this water, was not always there. It formed through a process called plate tectonics, the slow movement of the giant rocky plates that make up Earth's outer shell. These plates drift at about the speed your fingernails grow, slow but relentless. Over hundreds of millions of years, they pulled apart, collided, and shifted, reshaping the surface of the planet again and again. The basin that would become the Arctic Ocean began opening up roughly 56 million years ago. Before that, the region looked completely different. The continents were arranged in other shapes. Shallow seas covered different parts of the world. The poles were warmer. Scientists believe the Arctic Ocean formed as the Eurasian plate, the massive slab of rock carrying Europe and Asia, slowly separated from the North American plate. As the plates pulled apart, the crust between them is called seafloor spreading, and it still continues today. Deep beneath the Arctic Ocean, there is an underwater mountain range called the Gackle Ridge. It runs for about 1,100 miles along the ocean floor, roughly from Greenland toward Siberia. This ridge is where two plates are still slowly moving apart. Molten rock, called magma, rises up through the gap and hardens into new ocean floor. The Arctic Ocean is, in the quietest and most patient way, still growing, still being made. The Gackle Ridge is one of the slowest spreading ridges on Earth. It moves at less than 1 inch per year, but over millions of years, that adds up. The ocean floor on either side of the ridge is made of rock that was once liquid, that once glowed orange and red in the darkness of the deep sea, and then cooled and hardened and became the ground beneath the coldest ocean on the planet. Fire made this frozen place. That is worth sitting with for a moment. The ocean floor itself is not flat. It is divided into several deep basins, separated by underwater ridges. The Lomonosov Ridge, a long underwater mountain chain, runs nearly 1,100 miles across the ocean floor, from Russia to Greenland, splitting the deep Arctic into two main sections. This ridge rises about 10,000 feet above the surrounding ocean floor in places. It is a mountain range that almost no one has ever seen, buried under miles of cold, dark water. And above that, a ceiling of ice. The Arctic Ocean holds about 3.4 million cubic miles of water. That number is almost impossible to picture, but it is roughly 1% of all the water in all of Earth's oceans combined. Small as oceans go, ancient as basins go, and shaped from the very beginning by fire moving slowly beneath the surface of a cooling world. And yet, for all its ancient rock and deep cold water, the Arctic Ocean is not a still or frozen thing. It breathes, not the way you and I breathe, but in its own slow, enormous way. Every year, the ice that covers the Arctic Ocean grows and shrinks, expands and pulls back, following the rhythm of the sun like a living creature responding to the light. This is called the seasonal ice cycle, and it is one of the most remarkable things happening on Earth right now, tonight, while you rest. age arrive. The sea ice covers roughly 6 million square miles. That is nearly twice the size of the entire United States. All of it white and flat and silent under a sky that has not seen the sun in months. The ice is not all the same. Some of it is new, formed just that winter. Scientists call this first-year ice. It is thinner, maybe 3 to 6 feet deep, and a brighter, cleaner white. But some of the ice is older. It has survived one summer, or two, or many more. This older ice, called multi-year ice, is thicker and harder, and a deeper, almost blue-white color. It has been compressed by time and cold into something dense and ancient-looking. Walking across old Arctic sea ice fields, by all accounts, like walking across something that has been there forever. Then the sun returns. In late spring, the light comes back to the Arctic. It comes back slowly at first, just a pale glow along the horizon. Then longer and longer each day, until the sun does not set at all. And when that light falls on the ice begins to melt. The edges pull back. Melt ponds, shallow pools of pale blue water, form on top of the ice surface. These pools are beautiful and strange, like mirrors scattered across a white plain. They also matter enormously. Because dark water absorbs sunlight, while white ice reflects it back into space. The more the ice melts, the more open water appears. The more open water appears, the more heat the ocean absorbs. The ocean warms a little more, and the ice melts a little faster. Scientists call this the ice albedo feedback. Albedo means reflectiveness. High albedo means a surface bounces sunlight away. Low albedo means a surface drinks it in. Ice has very high albedo. Open ocean water has very low albedo. So as the ice retreats each summer, the Arctic Ocean absorbs more heat than it did before. It is a self-reinforcing cycle. One of the ways the Arctic is deeply connected to the temperature of the entire planet. By September, the sea ice reaches its smallest point of the year. In a typical year, before recent decades of warming, that summer minimum covered roughly 3 million square miles. Still vast, still cold, still ancient looking at its core, where the oldest multi-year ice survives. Then the cold returns. This breathing has been happening for millions of years, long before any human eye ever saw the Arctic. The ice was growing and shrinking with the seasons, following the tilt of the earth and the angle of the sun. The Arctic Ocean has been doing this since it first became cold enough to freeze, roughly 2 to 3 million years ago, during a period of global cooling that scientists call the Pleistocene epoch. Before that, evidence suggests the Arctic Ocean was far warmer. There may have been times when it held no permanent ice at all. The ice we think of as permanent, as defining, as simply the way the Arctic is actually a relatively recent feature of this planet. In the long story of Earth, it is something new, a response to shifting conditions, a sign of where the planet was climatically for the last few million years. And the ice is not just frozen water sitting on top of an ocean. It is a habitat, a ceiling for the creatures below, and a floor for the creatures above. It is a reflector that helps keep the whole planet cool. It is a record of seasons going back thousands of years, layer by layer, crystal by crystal. It breathes with the seasons, and in that breathing, it helps regulate the air that every living thing on Earth depends on. Beneath all of that ice, beneath the slow breathing of the frozen surface, there is an ocean. And that ocean is made of something remarkable. It is made of water, yes, but water itself is one of the strangest substances in the known universe. Most liquids get denser as they cool and sink to the bottom. Water does something different. When it freezes, it becomes less dense than its liquid form. It floats. That single, quiet fact changes everything. It means ice forms at the surface rather than the bottom. It means the ocean beneath stays liquid. It means life can survive in the dark water below, even when the surface above is locked in frozen silence. The water in the Arctic Ocean carries salt. On average, the Arctic is less salty than other oceans. This is partly because so many rivers pour fresh water into it, and partly because melting ice releases fresh water directly into the sea. Salt changes how water behaves. It lowers the freezing point. It increases density. A teaspoon of Arctic seawater holds roughly 28 to 32 grams of dissolved salt per kilogram of water. is small, but in the physics of an ocean, small differences shape entire systems. That salt did not come from nowhere. It leached slowly from rock. Over billions of years, rain fell on land, dissolved minerals from stone, and rivers carried those minerals to the sea. The ocean has been collecting salt since water first pooled on this planet, roughly 4 billion years ago. The calcium, the magnesium, the sodium, the chloride in Arctic seawater all came from the slow grinding of the continents. The ocean is, in a sense, a record of every rainstorm that ever fell on every mountain that ever stood, and the minerals in those mountains, the iron and calcium and silicon in the rock beneath the Arctic seafloor. Those elements were not made on Earth. They were forged in the cores of dying stars long before our sun existed. When a massive star reaches the end of its life, it collapses and then explodes in a burst of energy called a supernova. In that explosion, heavy elements scatter across space. Clouds of gas and dust drift for millions of years. Then gravity pulls them together again. New stars form. New planets form around those stars. The iron in the basalt beneath the Arctic Ocean, the calcium in the shells of Arctic clams, the silicon in the sand on the seafloor. All of it was made in stellar fire and scattered across the galaxy before the Earth was even born. The water itself may have traveled just as far. Scientists believe a significant portion of Earth's water arrived from space, carried by comets and asteroids during a period of heavy bombardment early in the planet's history. Comets are essentially dirty snowballs, frozen water and dust drifting through the outer solar system. When they struck the young Earth, they delivered their ice. That ice melted. It became oceans. Some of the water in the Arctic Ocean may have begun its existence as a comet falling through the darkness of space, billions of years before the first fish ever swam. Dissolved in that ancient water are gases. The Arctic Ocean holds oxygen, which marine animals breathe through their gills. It holds carbon dioxide, which tiny ocean plants use to grow. The exchange of gases between the ocean and the atmosphere is constant and invisible. The Arctic Ocean absorbs carbon dioxide from the air above it. water holds more dissolved gas than warm water. So the cold Arctic surface is especially good at pulling carbon out of the atmosphere and drawing it down into the deep. The ocean acts as a kind of slow, patient lung, breathing carbon in and holding it. The seafloor beneath the Arctic holds sediment, layer upon layer of it, built up over millions of years. Tiny organisms live and die in the water above. Their shells and skeletons drift slowly downward like a soft, endless snow. They settle on the bottom. They compress. They become rock. Scientists drill into that sediment and read it like a book, finding records of ancient temperatures, ancient ice ages, ancient blooms of life. The bottom of the Arctic Ocean is a library written in calcium and clay. Everything in that ocean, the salt, the minerals, the water, the gases, the sediment, connects back to something larger, to rivers and rain, to ancient rock and older stars. The Arctic Ocean is not just a body of water sitting at the top of the world. It is a gathering place for matter that has traveled unimaginable distances across unimaginable time, finally at rest, for now, beneath a ceiling of ice. Beneath that ceiling of ice, the water is not one single thing. It is many things stacked on top of each other, each layer with its own temperature, its own saltiness, its own quiet character. These layers do not mix easily. They hold their shape, and the force that keeps them apart is one of the most important and least visible forces in the entire Arctic Ocean. Salt makes water heavier. That is the simple truth at the heart of it. A cup of salt water weighs more than a cup of fresh water. So when you pour fresh water onto salt water, the fresh water floats. It sits on top, lighter, like oil on a pan. The Arctic Ocean receives enormous amounts of fresh water every year, from rivers, from melting ice, from rain and snow. All of that fresh water spreads across the surface and stays there because it is simply too light to sink. This creates something scientists call the halocline. The halocline is a sharp boundary layer in the ocean where saltiness changes quickly over a short distance. In most parts of the world's oceans, this kind of boundary is thin and unstable. But in the Arctic, the halocline is thick 200 meters below the surface, a hidden wall built entirely out of the difference between fresh and salty water. What makes the Arctic halocline so remarkable is what it protects. Below it, there is a layer of water that is actually warmer. This seems strange at first. Colder water near the surface, warmer water below. But that warmer water is also much saltier, and salt wins. The heavy, salty, warm water stays down. The lighter, fresher, cold water stays up. The halocline sits between them like a lid on a pot, keeping the warm water locked away from the surface. This matters enormously for the ice. If that warmer water below could rise and reach the surface, it would melt the sea ice from underneath. The halocline prevents that. It acts as a kind of shield, holding the cold surface water in place, allowing ice to form and survive through the winter. Without the halocline, the Arctic, as we know it, might not exist. The ice would thin, the surface would warm. Everything that depends on that ice, the seals, the polar bears, the microscopic algae living in the frozen brine, would feel the change. The halocline is not perfectly still. It moves slowly in response to the seasons. In summer, more fresh water pours in from rivers and melting ice, and the halocline strengthens. In winter, when sea ice forms, something interesting happens in reverse. As seawater freezes, it pushes its salt out. The ice itself is nearly fresh, but the water just below the forming ice becomes saltier and heavier. This dense, cold, salty water begins to sink. It slides downward through the halocline and into the deep. Scientists call this process brine rejection, and it is one of the engines that drives the slow circulation of the entire world's oceans. Think about that for a moment. Ice forming at the top of the world pushes cold, salty water down into the deep. That water travels. It joins the slow global current that moves through every ocean on Earth, carrying cold and oxygen and nutrients across thousands of miles over hundreds of years. The Arctic is not just sitting still. It is actively pumping, sending its cold water out into the world like a slow, steady heartbeat. The layers of the Arctic Ocean each carry different amounts of oxygen, different temperatures, different communities of life. The cold surface layer is rich in oxygen and supports the tiny plants and animals that form the base of the food web. The warmer, saltier layer below is older water, water that has been down there longer, water that has traveled from other oceans far away. Scientists trace these water masses the way a detective follows footprints, measuring temperature and salt and tiny chemical signatures to understand where each layer came from and where it is going. The Arctic Halocline is a force as real as gravity or wind. It shapes what lives and what dies in these waters. It controls whether ice forms or melts. It connects the surface of the ocean to its deepest parts, and those deep parts to the rest of the world. It is invisible to anyone standing on the ice above, looking out at the flat white horizon, but just below their feet, hidden in the dark and the cold, these layers of water are doing something extraordinary. They are holding the Arctic together, one quiet boundary at a time. Those hidden layers of water do something else remarkable. They carry something into the Arctic that most people never think about: fresh water. Not just from the ocean itself, but from the land, from rivers, from snow melting off mountains thousands of miles away. The Arctic Ocean receives more river water compared to its size than any other ocean on Earth. That single fact changes everything about how this ocean works. Think about the size of the Arctic Ocean for a moment. It covers about 5.4 million square miles. That sounds enormous. But among the world's 5 oceans, it is the smallest by far. The Pacific Ocean is nearly 14 times larger. If the Pacific were a king-sized bed, the Arctic would be a single pillow sitting in the corner. Small, yes, but fed by rivers in a way that no other ocean can match. Some of the longest rivers on Earth empty into the Arctic. The Ob, the Yenisei, and the Lena rivers in Russia are among the biggest rivers in the world. The Mackenzie River drains a huge portion of Western Canada. The Yukon River carries snowmelt from Alaska. Together, these rivers pour roughly 4,200 cubic miles of fresh water into the Arctic Ocean every single year. That number is hard to hold in your mind. So think of it this way. Imagine filling Niagara Falls letting it run without stopping. It would take the falls more than 6 years to move that much water. The rivers do it in 12 months. All that fresh water matters deeply. Fresh water is lighter than salt water. It floats. When rivers pour into the Arctic, they add a thin, cold, fresh layer right at the surface. This is part of what feeds the halocline, that hidden boundary between layers that was holding the Arctic together just a moment ago. The rivers are not separate from the ocean's inner life. They are part of it. They are constantly refreshing the surface, keeping it lighter, keeping it colder, helping ice form each autumn when temperatures fall. The Lena River alone is worth pausing on. It is one of the longest rivers in the world, stretching nearly 2,800 miles across Siberia before it reaches the Arctic coast. When it arrives, it fans out into a delta, a wide, flat spread of channels and islands that covers nearly 12,000 square miles. That delta is bigger than the state of Maryland. It is one of the largest river deltas on the planet. In spring, when the ice breaks up, the Lena pushes enormous chunks of river ice out into the Arctic Ocean. Those chunks drift and melt, releasing their fresh water slowly, like a quiet gift delivered over weeks. The rivers also carry something else: sediment, the fine particles of sand and silt and clay that wash off the land. The Mackenzie River alone carries about 130 million tons of sediment into the Arctic each year. When that sediment settles to the ocean floor, it builds up in layers over thousands of years. Scientists drill into those layers the way you might read rings in a tree trunk. Each layer tells a story about what the climate was like when it was deposited. Wet years, dry years, warm years, cold years. The ocean floor holds a record of the past that goes back millions of years, written in mud. There is something quietly moving about this. The rivers begin their lives in the hearts of continents, in mountain snowfields and forest lakes and frozen tundra. They travel hundreds or thousands of miles, picking up the memory of the land as they go. And then they arrive at the Arctic Ocean and give everything they have carried to the sea. The ocean receives it all. The fresh water, the sediment, the cold, the nutrients washed off the land. Nothing is wasted. This constant flow of river water also affects the ocean's salt levels in ways that ripple outward. The Arctic is less salty than most oceans because of all this fresh water pouring in, and that lower salt content affects how the water moves, how ice forms, and how the Arctic connects to the Atlantic and Pacific Oceans that border it. Change the rivers, and you change the ocean. Change the ocean, and you change the ice. Change the ice, and you change the climate of the entire northern half of the planet. The rivers and the ocean are not two separate things. They are one continuous system, passing water back and forth across the boundary where land meets sea. Standing at the Arctic coast, watching a river empty into the gray water, you are watching something ancient and ongoing. The land is always talking to the ocean, and the ocean, patient and vast, is always listening. Now lift your eyes from the water. Look up, because the sky above the Arctic Ocean tells its own story, and it is one of the strangest and most beautiful stories on Earth. Most places on our planet follow a simple rhythm. The sun rises, the sun sets. Day and night trade places every 24 hours, steady and reliable like breathing. But the Arctic does not follow that rhythm. The Arctic plays by different rules entirely. The Earth tilts on its axis, that invisible line running through the planet from pole to pole. That tilt is what gives us seasons. And at the top of the world, that tilt creates something that feels almost impossible the first time you hear it. For part of the year, the sun never sets. It circles the sky in a slow, low arc, dipping toward the horizon, but never crossing it. Day after day, the light continues. This is called the midnight sun. Stand on the ice of the Arctic Ocean in June, and you can watch the sun at midnight. It hangs low and golden, casting long shadows across the frozen surface. The ice glows. It turns pale gold, then orange, then a soft rose color as the sun dips toward the horizon, and then climbs again without ever disappearing. The sky never goes dark. The stars never appear. The world is suspended in a kind of endless amber afternoon that stretches on for weeks. At the North Pole itself, the sun rises once a year, around the spring equinox, is the other half of the Arctic year, the long dark. During the polar night, the sun stays below the horizon for weeks or months at a time, depending on how far north you are. At the North Pole, the darkness lasts from late September all the way to late March. Half a year without a sunrise. The sky overhead shifts through deep blue and purple and black. Stars appear that never set, circling slowly around the pole. The moon rises and sets, but the sun is gone. The surface of the Arctic Ocean during the polar night is a place of extraordinary quiet. The ice stretches out in every direction, pale and blue-gray under the starlight. There is almost no color, just the faint shimmer of ice, the dark patches of open water, and above it all, a sky thick with stars that most people on Earth never see so clearly. The air is so cold and so dry that the atmosphere barely scatters the light. The stars are sharp and still, and sometimes, during the long dark, something else fills the sky. A faint green shimmer appears near the horizon. It brightens. It ripples. Curtains of green and white light begin to move across the sky in slow, flowing waves. This is the Aurora Borealis, the northern lights, and we will spend much more time with it later in this journey. For now, just picture it. Green fire moving silently above the frozen ocean, reflected in the dark water between the ice floes below. The shift between the midnight sun and the polar night is not sudden. It happens gradually over weeks. The days grow longer and longer through spring until the sun stops setting. Then through late summer and fall, the sun dips lower and lower each day, the nights growing longer, until finally the sun disappears below the horizon and the darkness takes hold. It is a slow, seasonal breathing, light and dark, expanding and contracting, year after year. This extreme cycle of light shapes everything in the Arctic. The plants that grow on the surrounding land rush through their entire life cycle during the brief, bright summer. The animals that live in and around the Arctic Ocean time their migrations, their feeding, and their breeding to the rhythm of the light. The ice itself responds to the sun, melting back in summer and growing again in winter. Even the color of the ocean surface changes with the seasons, from the bright white of maximum ice cover in late winter engine that drives the Arctic year. Everything up here runs on light, or the absence of it. The ocean, the ice, the animals, the weather, all of it pulses to this slow, ancient rhythm of a tilted planet circling its star. But the light is only part of the story. Above the Arctic Ocean, the air itself is doing something remarkable. The Arctic is home to one of the most powerful weather systems on Earth. It is called the polar vortex. This is a massive ring of cold, spinning wind that circles the North Pole high up in the atmosphere. It sits roughly 10 to 30 miles above the surface in a layer of the atmosphere called the stratosphere. Think of it as a giant, invisible top, spinning slowly above the top of the world. The polar vortex is not a storm. It is more like a wall of fast-moving cold air that keeps the most extreme Arctic cold locked in place over the pole. When this spinning wall is strong and tight, the cold stays where it belongs. The Arctic stays cold. The regions farther south stay relatively mild, but sometimes the vortex weakens. It wobbles. It stretches out of shape. When that happens, tongues of bitterly cold Arctic air can spill southward, pouring down into North America, Europe, and Asia. People thousands of miles from the Arctic suddenly feel temperatures drop far below what is normal for their region. A weakened polar vortex is why some winters bring sudden, shocking cold snaps to places that rarely see such extremes. The Arctic does not keep its cold to itself. When the vortex breaks down, it shares. Scientists are studying whether the warming of the Arctic is making the polar vortex weaker and more unstable. The evidence is not yet settled, but the question matters enormously. The Arctic and the rest of the world are connected in ways that are still being mapped. Closer to the surface, the Arctic Ocean is shaped by a different set of winds. Persistent winds blow across the ocean in a slow, circular pattern, driven by the rotation of the Earth and the geography of the surrounding land. These surface winds push the sea ice around. They push water around. They help create something called the Beaufort Gyre, a slow clockwise circulation of water and ice in the western Arctic Ocean. The gyre acts like a slow spinning drain, gathering fresh Scientists estimate the Beaufort Gyre stores an enormous amount of fresh water, sometimes described as enough to significantly affect ocean circulation if it were suddenly released. The winds also create something called leads. A lead is a crack or channel of open water that forms in the sea ice when wind and currents pull the ice apart. These dark ribbons of open water can appear suddenly, stretching for miles across what looked like a solid, frozen surface. Leads matter enormously to the life of the Arctic. Seals use them to breathe. Polar bears hunt along their edges. Seabirds land on them to feed. A lead is a wound in the ice, and the whole ecosystem gathers around it. When winds push ice together instead of apart, the opposite happens. The ice buckles and folds, pushing up into jagged ridges called pressure ridges. These can rise several feet above the flat surface of the ice, like small frozen mountain ranges scattered across the sea. Below the surface, the ice pushes down even further, forming deep keels of ice that can reach 30 feet or more below the waterline. These underwater ridges scrape along the shallow seafloor in some parts of the Arctic, carving grooves into the sediment below. The wind, then, is not just weather. It is a sculptor. It shapes the ice, moves the water, and carves the seafloor. It connects the atmosphere above to the ocean below in a continuous, slow conversation. There is something humbling about this. The Arctic Ocean is not simply a body of water sitting quietly under a layer of ice. It is a dynamic, layered system. The winds above push the ice. The ice shapes the water beneath it. The water carries heat and salt in slow, invisible rivers. The cold air above locks the whole system in place, or releases it, depending on the strength of that great spinning wall of wind far above. Every layer is talking to every other layer. The atmosphere speaks to the ice. The ice speaks to the ocean. The ocean speaks back to the atmosphere through the heat it releases and the moisture it gives up. It is a system so deeply connected that pulling on one thread changes everything else, and all of it, every gust and gyre and pressure ridge and polar vortex, begins with the same simple fact. This is the coldest, most remote ocean on Earth, is one of the most powerful forces in the world. Cold does something remarkable to water. It makes it heavy, and heavy water sinks. This sounds simple, but this simple fact drives one of the most powerful systems on Earth. It is a system that moves heat from the tropics to the poles and back again. Scientists call it Halocline circulation, therma for heat, haline for salt. Together, heat and salt control how dense ocean water is, and density controls where water goes. Here is how it works. Warm water near the equator is light. It floats at the surface and drifts slowly toward the poles. As it travels north, it cools. Cold water is denser than warm water, and salty water is denser than fresh water. In the Arctic, both things happen at once. The water cools dramatically, and as sea ice forms, it pushes salt out into the surrounding ocean, making that water saltier and heavier still. Eventually, the water becomes so dense that it can no longer stay at the surface. It sinks. It sinks thousands of meters down into the deep ocean, and it begins a slow journey southward along the ocean floor. This sinking happens in only a few places on Earth. The North Atlantic, near Greenland and the Norwegian Sea, is one of them. The waters around Antarctica are another. These are the engine rooms of global ocean circulation. The cold, salty, heavy water that plunges downward in these places pulls warm surface water in behind it, like a drain pulling water across a bathtub. That pull is part of what drives the Gulf Stream, that great river of warm water that flows up the eastern coast of North America and across the Atlantic toward Europe. The Gulf Stream is famous, but the Arctic plays a quieter, equally important role. The cold water that forms here and sinks into the deep is sometimes called North Atlantic deep water. It is dense, dark, and oxygen-rich. It flows southward along the ocean floor for centuries before it eventually rises again in distant parts of the world. Scientists have traced water that sank near Greenland and found it rising again near Antarctica, or in the Indian Ocean, or in the Pacific. The journey takes hundreds of years. The water you see in the Arctic today may not reach the surface again until long after every person alive right now is gone. This slow, global movement of water is sometimes called the ocean conveyor belt. It carries more than just water. It carries heat. It carries nutrients. It carries dissolved oxygen that deep-sea creatures depend on to survive. The cold, sinking Arctic water is one of the main drivers of this whole system. Without it, the conveyor slows. And when the conveyor slows, the whole planet feels it. There is evidence that this has happened before. During past ice ages, massive amounts of fresh meltwater flooded into the North Atlantic from melting glaciers. Fresh water is lighter than salt water. It does not sink. It sits at the surface and acts like a lid, blocking the normal sinking process. Scientists believe this disrupted the conveyor belt dramatically. Parts of Europe cooled sharply, even as the rest of the world was warming. The system was thrown out of balance. It took centuries to recover. The Arctic Ocean sits at the heart of this rhythm. It breathes in a cycle measured not in days or seasons, but in centuries. Water sinks here. Water travels. Water rises somewhere far away. New water flows in to replace it. The cycle turns slowly, continuously, like the long, slow turning of a wheel that never stops. And the cycle does more than move water. It moves heat around the planet in a way that keeps climates stable. The tropics do not overheat. The poles do not freeze beyond all recovery. The system balances itself, constantly redistributing energy across the face of the earth. Every ocean is part of this. Every sea, every current, every river of warm or cold water flowing beneath the surface. But the Arctic is where the cold end of the cycle lives. It is where warm water comes to cool, to sink, and to begin its long journey home. There is something deeply calming about this. The ocean has been running this cycle for millions of years, long before humans arrived, long before the first fish swam in the sea. The water has been circling, sinking, rising, circling again. Patient and vast and utterly indifferent to the passage of time. The Arctic Ocean is not just cold. It is the cold that keeps the world in motion. And that cold, that weight, that slow sinking pull is the heartbeat of something much larger than itself. Beneath all of that cold, of ocean currents. Something is alive, something small and patient and extraordinary. The underside of Arctic sea ice is not bare. It is covered in life. Thin layers of algae, tiny golden brown organisms, no bigger than a grain of sand, cling to the bottom of the ice like a living carpet. These are ice algae, and they are the foundation of nearly everything that eats in the Arctic Ocean. They grow in the thin film of cold water just below the frozen surface, where a little light still filters through. In the early spring, when the sun returns after months of darkness, these algae bloom. The underside of the ice glows faintly gold and brown, and the Arctic begins to feed. Ice algae produce energy through photosynthesis, the same process plants use to turn sunlight into food, but they do it in temperatures that would stop most living things cold. Scientists have found these algae thriving at temperatures just below freezing, clinging to ice that is shifting and cracking above them. They are among the toughest living things on Earth. Tiny shrimp-like creatures called copepods, no larger than a grain of rice, feed on the algae. They gather in enormous numbers beneath the ice, grazing slowly through the cold water. A single cubic meter of Arctic water can hold thousands of them. They are almost invisible to the naked eye, but together they form one of the largest masses of animal life in the ocean. Everything above them in the food chain depends on them. Arctic cod eat the copepods. Seals eat the cod. Polar bears eat the seals. The whole chain starts here, in the dark, cold water beneath the ice, with something smaller than a fingernail. Arctic cod are worth pausing on. These small silver fish are perfectly built for the cold. They carry a kind of natural antifreeze in their blood, special proteins that stop ice crystals from forming inside their bodies. Scientists call these antifreeze proteins, and they work by binding to tiny ice crystals before those crystals can grow large enough to damage cells. The cod can swim through water that is technically below the freezing point of ordinary seawater. They live and hunt in places that would kill most fish within minutes. The cod gather in huge schools beneath the ice, feeding on copepods and small crustaceans. They are not alone down there. The under-ice world is crowded with life. Amphipods, small crustaceans, cling to the rough underside of the ice itself. They graze on algae and hide in the cracks and ridges of the frozen surface above them. Ringed seals, the smallest seals in the Arctic, dive down through holes in the ice to hunt the cod. They are fast and quiet. They can hold their breath for over 40 minutes. They navigate by sound in the dark water, listening for the movement of fish below them. The ice itself shapes all of this. The ridges and pressure ridges on the underside of sea ice, formed when ice sheets push against each other and buckle, create a rough and complex surface. That rough surface gives amphipods and other small creatures places to hide and hold on. Smooth ice would offer far less shelter. The physical structure of the ice, the way it breaks and refreezes and piles up, directly determines how much life can shelter beneath it. The ice is not just a lid on the ocean. It is a habitat, and the relationship runs in both directions. The algae growing beneath the ice help regulate the chemistry of the water around them. As they photosynthesize, they absorb carbon dioxide from the water. This small but constant process helps the Arctic Ocean absorb carbon from the atmosphere above. The algae are not just food. They are part of the ocean's chemistry, part of the planet's carbon cycle, part of the slow breathing of the Earth itself. When summer comes and the ice melts, the algae release from the ice and sink slowly through the water column. They carry their stored energy downward, feeding creatures in the midwater, and eventually reaching the seafloor far below. The energy that started as sunlight filtering through ice ends up at the bottom of the ocean. Nothing is wasted. The whole system passes energy from one layer to the next, from the surface to the deep, from the smallest organism to the largest predator. Life under the ice is quiet and hidden and easy to overlook. But it is the engine of the Arctic. Without it, the seals would not eat. The bears would not hunt. The whole frozen world above would grow silent. That energy carried down from the ice above does not fall into emptiness. It falls into a world that most people never imagine exists. The floor of the Arctic Ocean is not a bare, cold desert. In places, it is alive with structure and color and strange, slow growth. knows there is among the oldest and most remarkable living things on Earth. Cold water corals grow on the Arctic seafloor. This surprises many people. Coral feels like a warm water creature, something bright and tropical, something belonging to shallow, sunlit seas. But cold water corals ask for none of that. They grow in near freezing water, in near total darkness, at depths where the pressure would crush a human body in seconds. They do not need sunlight. They feed on the tiny particles of organic matter that drift down from above, including the very algae that fell from the melting ice. The energy from the surface reaches them, even here, even in the dark. These cold water coral structures grow very slowly. Some of the coral reefs found in the deep North Atlantic and Arctic regions are thousands of years old. A single coral colony might grow only a few millimeters each year. Over centuries, those millimeters become meters. Over millennia, they become sprawling, branching structures that rise from the seafloor like frozen trees. Scientists sometimes call them cold water coral gardens, and the name fits. They have the quiet, branching complexity of a forest in winter. These gardens do not just look like forests. They function like them. Hundreds of species shelter inside coral structures. Small fish hover near the branches. Crustaceans, the hard-shelled creatures like crabs and shrimp, tuck themselves into gaps in the coral. Worms and sea stars and sponges attach themselves to the surface. One coral garden can support more species than the surrounding bare seafloor by a factor of many times over. The structure itself creates the conditions for life. It gives creatures a place to hide, to feed, to reproduce. Without the coral, the seafloor would be far emptier. Sponges also grow on the Arctic seafloor, and they are record breakers in their own right. Some Arctic sponge species are among the longest-lived animals on the planet. Scientists have found sponges in cold, deep waters that are estimated to be over 10,000 years old. 10,000 years. That means some of these animals were alive before the first human cities were built. They were alive when woolly mammoths still walked the earth. They sit on the seafloor, completely still, filtering tiny particles from the water. And they have been doing exactly that for longer than recorded human history. The seafloor of something called manganese nodules. These are small, dark, rounded lumps of mineral that form very slowly on the ocean floor. They grow around a tiny piece of material, a fragment of shell or bone or rock, and over millions of years, layers of manganese and iron and other minerals build up around that core. The nodules grow at a rate of about 1 to 2 millimeters every million years. They are among the slowest forming objects on Earth. The Arctic seafloor holds vast fields of them, scattered across the sediment like dark stones in a quiet garden. The sediment itself tells a story. Arctic seafloor mud contains layers that record the history of the ocean above. Scientists drill into this sediment and pull up cores, long cylinders of layered material that hold records of ancient ice ages, ancient warm periods, ancient changes in ocean chemistry. Each layer is a chapter. The deepest layers are millions of years old. The seafloor remembers what the surface has long forgotten. And then there are the hydrothermal vents. These are cracks in the seafloor where superheated water, warmed by the heat of the Earth's interior, pours out into the freezing ocean. The Arctic has its own vent systems, including fields along the mid-ocean ridge that runs beneath the Arctic Basin. At these vents, water can reach temperatures of several hundred degrees Celsius, though the pressure keeps it from boiling. Around these vents, entirely separate communities of life exist. Bacteria that feed on chemicals rather than sunlight form the base of these food webs. Shrimp and worms and other creatures cluster around the vents, thriving in conditions that would be lethal to almost anything else. The floor of the Arctic Ocean is not a dead place. It is a layered, ancient, extraordinary world. It holds creatures older than civilization. It holds minerals that took millions of years to form. It holds records of the planet's deep past. The surface of the Arctic may be what we see, but the floor is what endures. Above the ancient seafloor, far from the vents and the sediment layers and the slow dark quiet of the deep, the water rises. It rises through cold and pressure and shadow, up through the Halocline, up past the ice keels that hang down like frozen chandeliers from the surface above. And here, in the middle and upper waters of the Arctic Ocean, the giants live. The bowhead whale is one of the largest animals on Earth. It can grow to nearly 60 feet long and weigh close to 100 tons. That is heavier than any land animal that has ever existed. But what makes the bowhead truly remarkable is not its size. It is its age. Scientists believe that some bowhead whales live for more than 200 years. Researchers have found old stone harpoon tips buried in the blubber of whales caught in recent decades. Those harpoon tips were made by indigenous hunters long before modern tools existed. The whale had been carrying that tip for well over a century. The bowhead swimming through Arctic waters today may have been alive when your great-great-grandparents were children. The bowhead's skull is built like a battering ram. It can be nearly a third of the animal's total body length. The whale uses this massive, arched skull to break through sea ice up to 2 feet thick. It simply rises from below and pushes. The ice cracks. The whale breathes. In a world where open water is never guaranteed, the bowhead carries its own solution. These whales feed on some of the smallest creatures in the ocean. Copepods are tiny crustaceans, smaller than a grain of rice, that drift through the Arctic water in enormous clouds. Krill, small shrimp-like animals, gather in dense swarms that can stretch for miles. The bowhead opens its enormous mouth and swims slowly forward, filtering millions of these tiny creatures through long, brush-like plates called baleen. The largest animal in the Arctic survives entirely on some of its smallest. That quiet balance runs through everything here. The walrus is another giant of these waters, though a very different kind. A large male walrus can weigh over 3,000 pounds. Its tusks, which are elongated canine teeth, can grow to 3 feet long. Both males and females carry them. The walrus uses its tusks to haul itself out of the water onto ice, to establish rank among other walruses, and to keep breathing holes open in thin ice. Those tusks are tools, weapons, and anchors all at once. Walruses feed on the seafloor. They dive down and use their sensitive whiskers, called vibrissae, to feel along the bottom in near total darkness. They find clams and other shellfish buried in the sediment. A single walrus can eat thousands of clams in one feeding session. Their lips create a powerful suction, pulling the soft body of the clam right out of its shell. The shell falls back to the seafloor. The walrus rises, breathing in the cold Arctic air, its pale tusks catching the low winter light. The bearded seal is smaller than the walrus, but it shares the same seafloor feeding strategy. It is named for the thick, drooping whiskers on its face. Those whiskers are extraordinarily sensitive. Scientists believe they can detect the tiny movements of prey buried in sediment. The bearded seal can find a clam in total darkness, under the ice, at depth, by feel alone. Its whiskers are one of the most precise sensing tools in the animal kingdom. There is something quietly astonishing about the scale of life in these waters. The Arctic Ocean covers about 14 million square kilometers. That is roughly the size of the entire continent of Antarctica. Within that vast, cold, often frozen space, creatures of enormous size and extraordinary age go about their lives with a kind of unhurried calm. The bowhead does not rush. The walrus rests on its ice floe for hours, eyes half closed, whiskers dripping. The bearded seal drifts just below the surface, watching the fractured light filter down through the ice above. These animals have been here for a very long time. The bowhead's ancestors swam these waters before humans built cities. The walrus has lived along Arctic coastlines for millions of years. They did not arrive here by accident. They were shaped by this place slowly, over vast stretches of time. Their thick blubber, their specialized feeding tools, their tolerance for cold and dark and ice. All of it came from living alongside the Arctic Ocean, generation after generation, until they fit this world like a hand fits a glove. The ocean made them, and in return, they are part of what makes the ocean whole. Humans were shaped by this place too. Long before any European sailor pointed a ship toward the frozen north, people were already living at the edge of the Arctic Ocean. They had been there for thousands of years. They knew its moods, its seasons, its animals, and its ice in ways that no written record could fully capture. Their knowledge was passed down in stories, in the names they gave to places, in the routes they walked and paddled across generations. eastward across northern Canada and Greenland roughly 1,000 years ago. They were not the first people in the far north, but they became the most perfectly adapted. They built homes from snow and ice. They hunted bowhead whales from small skin boats. They read the surface of sea ice the way a sailor reads the sky, looking for cracks, for color changes, for the subtle signs that told them where it was safe to walk and where it was not. Their routes across the frozen ocean were not random. They were roads, carefully learned and carefully remembered. These migration roads followed the animals. The bowhead whale moved with the seasons, and the hunters moved with the bowhead. The caribou crossed the tundra in great flowing herds, and the people followed. The Arctic tern flew its impossible path from pole to pole, and even that bird was known and named. The far north was not a blank, empty wilderness. It was a world full of meaning, mapped in memory and motion. European explorers arrived much later, and they arrived poorly prepared. The first serious attempts to chart the Arctic Ocean came in the 1500s and 1600s, when English and Dutch sailors pushed north, looking for a shortcut to Asia. They found ice instead. Many of them did not come back. The ships that did return brought stories of crushing cold, of sea ice that closed around a vessel like a fist, of darkness that lasted for months. These were not exaggerations. The Arctic Ocean was genuinely dangerous to people who did not know it. But the expeditions kept coming. In 1596, the Dutch explorer Willem Barents sailed north of Norway and reached the island of Spitsbergen, which sits deep inside the Arctic Circle. His ship was eventually trapped in the ice near the island of Novaya Zemlya, off the northern coast of Russia. His crew spent an entire winter there, surviving in a wooden hut they built from driftwood and ship timber. Barents himself did not survive the journey home. He died at sea in 1597, but his maps, his journals, and the records his crew kept helped chart a part of the Arctic that Europeans had never seen before. The sea north of Norway and Russia still carries his name today, the Barents Sea. Other expeditions followed, each one adding a little more detail to the picture. Henry Hudson sailed into the Arctic in north before ice turned him back. His observations of the sea, the ice, and the wildlife were among the most detailed of his time. He noted the presence of whales in enormous numbers. That observation, unfortunately, helped launch the commercial whaling industry that would hunt Arctic bowhead populations to the edge of collapse over the next 2 centuries. The true scientific mapping of the Arctic Ocean came slowly, across many expeditions and many nations. Russian explorers charted the long northern coast of Siberia during the 1700s, a project so enormous it took decades and cost many lives. The Great Northern Expedition, led by Vitus Bering, sent ships and overland parties across thousands of kilometers of frozen land and sea. They mapped coastlines, measured ocean depths, and recorded the wildlife they encountered. Bering himself died on an island in the sea that now bears his name, stranded by storms on his return voyage in 1741. What these explorers slowly pieced together over centuries of effort and loss was a picture of an ocean that was not simply a barrier or a dead end. It was a living system, connected to the rest of the world's oceans, shaped by forces that reached far beyond its frozen surface. They could not yet explain those forces. The science of oceanography was still young, but they were beginning to ask the right questions. And all the while, the Inuit and other Arctic peoples already held answers that the explorers had not thought to seek. The migration roads of the far north were older than any European map. They were drawn not in ink, but in footsteps, in paddle strokes, in the long memory of people who had made this frozen ocean their home. Those Arctic peoples knew something that took Western science a very long time to accept. The Arctic Ocean is not empty. It is not a frozen wasteland between continents. It is full of life, and some of that life is so strange, so perfectly shaped by millions of years of cold and darkness, that it seems almost invented. Consider the narwhal. The narwhal is a whale. It lives in the cold, deep waters of the Arctic Ocean, mostly around Canada, Greenland, and Russia. It grows to about 5 meters long, and from the front of its head, a single long tusk spirals outward, sometimes reaching 3 meters in length. For centuries, centuries, people in Europe had never seen a narwhal, but they found the tusks brought back by traders and sailors. They believed those tusks came from unicorns. The tusks were sold for enormous sums of money. Kings and queens kept them as treasures. The Danish throne, built in the 1600s, was constructed partly from narwhal tusks, believed at the time to be the horns of mythical creatures. The tusk is actually a tooth. It grows from the upper left jaw of the male narwhal, spiraling in a left-handed twist almost every time. Scientists debated for years what the tusk was actually for. It seemed too long and fragile for fighting, too exposed for breaking ice. Then researchers discovered something remarkable. The tusk is packed with nerve endings, millions of them, running all the way to the surface. It can sense changes in water temperature, salt levels, and pressure. The narwhal, in other words, carries a giant sensory instrument on its face. It reads the ocean through its tooth. Female narwhals almost never grow a tusk. Yet females live longer than males and survive the Arctic just as well. This tells scientists the tusk is not essential for survival. It may play a role in how males attract mates, but the full story is still being pieced together. The narwhal keeps its secrets well. Not far from the narwhal's range lives another whale that surprises almost everyone who learns about it. The beluga is small for a whale, about 4 to 5 meters long, and it is white, completely softly white, like a cloud drifting through dark water. Young belugas are actually gray or brownish when they are born. They turn white slowly as they age, reaching their full pale color by the time they are about 7 years old. No one is entirely sure why belugas are white. Some scientists believe the color helps them blend into ice-covered water. Others think it may help them regulate heat or play a role in how they recognize each other. Belugas can do something almost no other whale can do. They can move their necks. Most whales have fused neck vertebrae, the bones of the spine, which means they cannot turn their heads. Belugas have unfused vertebrae, so they can tilt and turn their heads in ways that look almost human. Watch a beluga in the water, and it will look back at you. It will tilt its head. It will seem is hard to explain, genuinely curious. Belugas are also among the most vocal animals on Earth. They produce clicks, whistles, chirps, squeals, and bell-like tones. Early sailors could hear them through the hulls of their wooden ships. They called belugas sea canaries. A group of belugas communicating beneath the ice creates a sound that fills the water like a slow, strange music. Both narwhals and belugas belong to a group called toothed whales, and both spend their entire lives in Arctic and subarctic waters. They dive deep, sometimes to 800 meters or more, hunting fish and squid in near total darkness. They navigate by echolocation, sending out pulses of sound and listening for the echoes that bounce back. The Arctic Ocean, so quiet on its surface, is alive with sound beneath the ice. What surprises scientists most is how social these animals are. Narwhals travel in groups, sometimes in the hundreds. Belugas gather in pods that can number in the thousands. They move together along ancient routes, following the same paths their ancestors followed, generation after generation. The routes shift slightly as the ice changes, but the animals adapt, reading the ocean the way the narwhal reads it through its tusk, with senses tuned over millions of years to this particular place. The Arctic Ocean shaped these creatures, and in small, quiet ways, these creatures shape the ocean too. They carry nutrients from the deep to the surface. They feed the bears and the people on the ice above. Every life here is woven into every other life, each one depending on the cold, the dark, and the slow turning of the seasons. And at the top of that chain, standing on the frozen edge where sea meets sky, is the polar bear. The polar bear is the largest land carnivore on Earth. A full-grown male can weigh over 700 kilograms. That is heavier than a small car. He stands nearly 3 meters tall when he rises on his hind legs. And yet, for all that size, he moves across the ice with surprising quiet. His wide, padded paws spread his weight, so he does not crash through thin ice. Each paw is slightly webbed, making him a strong swimmer too. He is built for this edge, this frozen border between ocean and air. The polar bear's world is the sea ice, not the land, not the open ocean. because he depends on the sea for his survival. He hunts almost entirely from the ice's surface, waiting beside breathing holes where ringed seals come up for air. That moment of stillness, the bear motionless above the hole, can last for hours. He is patient in a way that is hard to imagine. The cold does not bother him. Beneath his white fur, his skin is actually black, absorbing what little warmth the Arctic sun provides. His fur is not truly white either. Each individual hair is hollow and transparent. The hairs scatter light in a way that makes the coat appear white or pale yellow against the snow. This is not camouflage in the way we usually think of it. It is something more elegant. The coat reflects the world around it, making the bear almost invisible against the ice he calls home. The ringed seal is the polar bear's main prey, and the ringed seal depends on sea ice too, using it as a platform to rest and raise its young. So the polar bear's survival is tied to the seal's survival, and the seal's survival is tied to the ice, and the ice is tied to the temperature of the Arctic Ocean, and the ocean's temperature is tied to currents that travel from the tropics and back again. Pull one thread, and the whole system feels it. This is what makes the Arctic so extraordinary. Every creature here exists because of a precise set of conditions. The ice forms at a certain temperature. The seals need the ice to pup. The bears need the seals to eat. The foxes follow the bears, scavenging scraps from kills. The ravens follow the foxes. Even the tiny amphipods, small shrimp-like creatures that live on the underside of sea ice, feed the fish that feed the seals. Nothing here is separate. Everything feeds into everything else. A long, slow chain of dependence stretching from the smallest organisms to the largest predator on the ice. The polar bear also connects the ocean to the land in a physical way. When a bear makes a kill out on the ice and drags it ashore, or when a bear dies on land, the nutrients from that marine animal enter the soil. Plants absorb them. Insects feed on the plants. Birds feed on the insects. The ocean's richness travels inland, carried by the bear, spreading outward in ways that are still being studied and understood. Female polar bears dig maternity dens in snowdrifts along the coast each autumn. they enter those dens pregnant and do not eat again until spring. Inside the den, in total darkness, they give birth to cubs that weigh less than half a kilogram. Tiny, blind, and helpless, the mother keeps them warm with her body heat, nursing them through the long winter while the ocean freezes solid outside. By spring, the cubs are strong enough to follow her out onto the ice. Their first lesson is how to hunt. Their classroom is the frozen sea. A polar bear's life is measured in ice. Good ice years mean fat bears and healthy cubs. Poor ice years mean longer swims, fewer seals, and thinner animals. Scientists have tracked individual bears swimming over 700 kilometers in a single journey, crossing open water in search of ice that used to be closer. The bear does not know why the ice has moved. It only knows to keep swimming. What the polar bear shows us, more clearly than almost any other animal, is that the Arctic Ocean is not just water and ice. It is a living system, one where the chemistry of the sea, the temperature of the air, the thickness of the ice, and the fate of a single species are all bound together. Change one thing, and the ripple moves outward in every direction, touching lives we might never have thought to connect. Those ripples reach far beyond the bear. They reach into the lives of people who have called the Arctic home for thousands of years. Long before any explorer from the south drew a map of these waters, human beings were already living beside them. The Inuit, the Yupik, the Inupiat, the Chukchi, and dozens of other indigenous peoples built entire ways of life around the Arctic Ocean. They learned its moods. They read its ice. They listened to it in ways that took generations to understand. Their knowledge of this place runs deeper than any scientific record we have. The Inuit, for example, have lived in the Arctic for roughly 4,000 years. They spread across an enormous stretch of the far north, from Siberia and Alaska all the way across Canada to Greenland. That is a distance of thousands of kilometers, and yet their cultures share deep roots. The sea connected them. The ice was their road. For these communities, the Arctic Ocean was never a wilderness. It was a pantry, a highway, a calendar, and a home. The ringed seal provided food, oil for lamps, and skins garments for clothing. The bowhead whale, one of the longest-lived animals on Earth, was hunted in ceremonies that treated the whale not as a resource, but as a gift. The hunt was surrounded by ritual and respect. Nothing was wasted. Every part of the animal fed or clothed or warmed someone. The sea ice itself was a tool. Hunters read its surface the way a sailor reads the sky. They knew which ice would hold weight and which would crack. They knew where the seals came up to breathe. And they knew this because they had watched and listened and learned. Season after season, generation after generation. This knowledge was passed down in stories, in songs, in the careful teaching of children on the ice. Indigenous languages of the Arctic contain dozens of words for ice and snow, each one describing a specific condition. There are words for new ice that bends underfoot, for old ice that has survived many summers, for ice that has been pushed up into ridges by wind and current, for ice that is safe and ice that is not. This is not poetry. It is precision. It is a technical vocabulary built by people whose lives depended on getting it exactly right. And now that vocabulary is being tested. The ice those words describe is changing. Elders across the Arctic report that the sea ice now behaves in ways their grandparents never described. It arrives later in the autumn. It breaks up earlier in the spring. It is thinner. It moves in unexpected ways. Ice that was once reliable is now dangerous. Hunting routes that families used for centuries are no longer safe to travel. This is not a distant or abstract change. It is immediate. A hunter who goes out on ice that used to be solid and falls through is not a statistic. He is a father, a son, a teacher of the next generation. The loss of reliable sea ice is a safety crisis, a food security crisis, and a cultural crisis all at once. Coastal villages in Alaska and Siberia are facing something even more dramatic. The sea ice that once lined the shore in winter acted like a wall. It protected the coastline from storm waves. As that ice disappears, the waves reach the shore directly. They eat into the land. Some villages, built on permafrost that is also thawing, are losing meters of coastline every year. Several communities have already voted to relocate entirely, moving their homes inland away from a shore that is no longer stable. And yet, through all of this, indigenous peoples of the Arctic remain. They are not simply victims of change. They are observers, scientists in their own right, and advocates. Many communities now work alongside climate researchers, sharing traditional knowledge that fills in the gaps of the scientific record. An elder who has watched the same stretch of coastline for 60 years carries data that no instrument can replicate. The relationship between indigenous peoples and the Arctic Ocean is one of the oldest continuous human relationships with any body of water on Earth. It stretches back through ice ages and warming periods, through migrations and adaptations that would astonish us if we could see them clearly. These communities survived because they were flexible, because they paid attention, and because they understood that the ocean and the ice and the animals and the people were all part of the same living whole. The Arctic has always changed, but it has rarely changed this fast. And the people who know it best are watching every shift with the quiet attention of those who have always known that this place demands respect. There is something almost invisible happening above the Arctic Ocean right now. Something that touches every person on Earth, no matter how far they live from the ice. The Arctic does not just sit quietly at the top of the world. It works. It regulates. It cools the entire planet like a vast, slow engine made of light and frozen water. It begins with color. The ice and snow that cover the Arctic Ocean are almost perfectly white, and white surfaces reflect sunlight back into space rather than absorbing it. Scientists call this quality albedo, which simply means how much light a surface bounces away. Fresh snow has an albedo of around 80 to 90%. That means nearly all of the sunlight that strikes it turns around and leaves. The Arctic, in this way, acts like a mirror held up to the sun. The ocean beneath that ice tells a very different story. Open seawater is dark, deep blue, almost black in certain light. Dark surfaces absorb sunlight rather than reflect it. The ocean drinks in heat where the ice would have sent it away. This difference between the bright mirror of ice is one of the most powerful forces shaping the temperature of the whole planet. When the Arctic holds its ice, it keeps that reflective surface large and bright. Sunlight bounces away. The planet stays cooler. When the ice shrinks, more dark water is exposed. More heat is absorbed. The planet warms a little more, and that extra warmth melts more ice, which exposes more dark water, which absorbs more heat. Scientists call this a feedback loop, a cycle where each step makes the next step stronger. The Arctic sits at the center of one of the most significant feedback loops on Earth. But the Arctic does more than reflect light. It also moves cold air and cold water outward toward the rest of the planet. The temperature difference between the warm tropics and the frozen Arctic drives the great wind systems that circle the globe. Warm air rises near the equator. Cold air sinks near the poles. That difference in temperature creates pressure, and pressure creates wind. The Arctic is one of the engines that keeps those winds moving. The cold water of the Arctic Ocean feeds into the global ocean circulation system, sometimes called the conveyor belt of the seas. Cold, dense Arctic water sinks deep and flows southward along the ocean floor. Warmer water from the south flows north along the surface to replace it. This constant exchange carries heat from the tropics toward the poles and sends cold water back the other way. It keeps places like Western Europe far warmer than they would otherwise be at their latitude. Without the Arctic doing its part, that circulation slows, and the effects ripple outward in ways that are still not fully understood. Light plays one more quiet role in all of this. During the Arctic summer, the sun stays above the horizon for weeks at a time. That long, low sunlight strikes the ice at a shallow angle. Even when the sun shines for 24 hours, its rays arrive sideways, spread thin across a wide area. This is why the Arctic summer, despite its endless daylight, stays cold. The sunlight simply does not carry enough concentrated energy to melt everything away. The geometry of the Earth protects the ice even while the sun is always shining. In winter, the opposite happens. The sun vanishes entirely. For months, the Arctic Ocean sits in complete darkness. freeze exposed skin in minutes. The ocean radiates its stored heat upward into the dark sky and grows colder still. That cold radiates outward, cooling the air masses that will eventually sweep down into the lower latitudes and bring winter to the rest of the world. The Arctic, then, is not simply a remote and frozen place. It is a thermostat, a regulator, a surface that manages how much of the sun's energy the Earth keeps and how much it sends back. Every degree of temperature on a warm afternoon in a city far from the poles was shaped, in part, by what the Arctic ice is doing at this very moment. The elders of the Arctic communities have always understood that this place is connected to everything. They did not have the language of albedo or ocean circulation, but they knew that the ice mattered, that the cold mattered, that what happened here sent ripples outward into a world that could not see where those ripples began. Science has simply found a way to measure what they already knew. Beneath the Arctic Ocean and spreading across the land that rings it, something ancient waits inside the ground itself. It is called permafrost. That name means exactly what it sounds like. Ground that stays permanently frozen, not just in winter, not just on the coldest nights. Year after year, decade after decade, century after century, the soil stays locked in ice. In some places, the permafrost reaches down more than 1,000 meters below the surface. It is one of the oldest and most patient things on Earth. Permafrost does not look dramatic from the outside. Walk across the tundra in summer, and the ground beneath your boots feels soft, even muddy. That is because the very top layer thaws a little each warm season. Scientists call this the active layer. It is only a thin skin, maybe a meter deep, that breathes with the seasons. Below it, the frozen ground begins, and it does not thaw. It has not thawed for thousands of years. Some of the permafrost beneath the Arctic was frozen during the last great ice age, more than 10,000 years ago. It remembers that cold. It has held that cold ever since. And inside that frozen ground, something remarkable is preserved. Ancient plants, old roots, insects, seeds, even the bodies of large animals locked in ice before they could decay. Scientists their skin still whole. The cold stopped time for them. The permafrost acted like a natural freezer, holding the past exactly as it was. Researchers have even found seeds frozen in permafrost for more than 30,000 years and successfully grown them into living plants. The ground remembered what the surface had long forgotten. Now think about what that frozen ground sounds like. Not the silence you might expect. Permafrost, when it shifts, makes noise. In the coldest months, the ground contracts as temperatures drop, and it cracks. Those cracks can run for hundreds of meters across the tundra, splitting the frozen earth with a sharp, rifle-like snap that echoes across the flat land. In spring, when the active layer begins to thaw, water moves through those cracks, and the ground settles with low, soft groans. The land itself speaks in the language of freezing and thawing. A slow conversation it has been having with the cold for millennia. Beneath the Arctic Ocean, the permafrost continues. On the shallow continental shelves, where the sea is not very deep, the ocean floor is also frozen. This is called subsea permafrost, and it formed long ago when sea levels were lower and those shelves were dry land. As the oceans rose after the last ice age, the sea covered that frozen ground. The cold water preserved it. It has been sitting there, submerged and frozen, ever since. Scientists believe the subsea permafrost on the East Siberian Arctic shelf is among the most extensive frozen ground on the planet, stretching across an area larger than the lower 48 United States. The permafrost holds something else inside it, trapped in the frozen soil and in the frozen ocean floor. There are enormous amounts of organic material, old dead plants, and animals that never fully decomposed because the cold stopped the process. As that material sits frozen, it holds carbon, vast amounts of carbon, built up over thousands of years of Arctic life and death. Scientists estimate that Arctic permafrost holds roughly twice as much carbon as is currently in the entire atmosphere. It is a storehouse, a vault, and the key to that vault is temperature. The sounds of permafrost thawing are subtle but real. In summer, across the Siberian and Alaskan tundra, the ground in some lakes, formed in the hollows left by collapsing frozen ground. The land ripples and sags. Trees in some boreal forests near the permafrost zone tilt at strange angles, their roots losing their frozen anchor, giving those forests the name scientists use informally: drunken forests. The ground is speaking again in a new and different voice. All of this connects back to the ocean. The rivers that drain the permafrost regions carry their thawed water into the Arctic Sea. The carbon stored in that ground moves with it. The chemistry of the water shifts. The temperature of the land around the ocean changes. The permafrost and the sea are not separate systems. They are one system, breathing together, holding the memory of an ice age in frozen silence, and now, slowly, beginning to speak. The numbers, when you sit with them quietly, tell a story all their own. In 1979, scientists began using satellites to measure the Arctic sea ice in a way that had never been possible before. From space, they could see the full white cap of the frozen ocean, stretching across millions of square miles. That first measurement gave us a baseline, a starting point. And every year since, the satellites have looked down and measured again. What they found is this: the Arctic sea ice reaches its smallest size each year in September, at the end of the summer melt season. In the late 1970s and early 1980s, that September minimum covered roughly 2.7 million square miles of ocean. That is an area larger than the entire continent of Australia. A vast, white, floating world. By 2012, that number had fallen to just 1.32 million square miles. That was the lowest ever recorded. Scientists measured it carefully, checked it twice, and confirmed it. In roughly 3 decades, the Arctic had lost about half of its summer sea ice. Not a fraction, not a small slice. Half. The rate of that loss is something scientists track with great care. On average, the Arctic is losing about 13% of its September sea ice every decade. That is a steady, measurable, consistent number. The kind of number that tells you something real is happening, not a random fluctuation. A trend, clear and steady as a drumbeat. There is another number that carries enormous weight, is warming roughly 4 times faster than the rest of the planet. Scientists call this Arctic amplification, meaning the warming effect is made stronger or amplified in the far north. The reason comes back to the ice itself. White ice reflects sunlight back into space. When ice melts and reveals dark ocean water beneath, that water absorbs sunlight instead of bouncing it away. The ocean warms, more ice melts, more dark water appears. The cycle feeds itself. One small change becomes a larger one. This is what scientists call a feedback loop, a process where the result of a change becomes the cause of further change. The mathematics of a feedback loop are simple. A small push, repeated, becomes a large force. The Arctic has entered one of these loops, and the numbers show it clearly. The thickness of the ice tells its own part of the story. Sea ice comes in 2 kinds. First-year ice forms each winter and melts each summer. It is thinner, typically around 3 to 6 feet deep. Multi-year ice is older ice that has survived at least 1 summer melt season. It is thicker, harder, and more resistant to warming, sometimes reaching 10 feet or more in depth. In the 1980s, multi-year ice made up roughly 60% of the Arctic's winter ice cover. Today, that number has fallen to around 30%. The old, thick ice is being replaced by young, thin ice. The Arctic is getting younger, in a way, and more fragile. The volume of ice, not just the area, but the total amount of frozen water, has dropped even more sharply than the surface measurements suggest. Scientists estimate that the total volume of Arctic sea ice has declined by about 75% since the 1980s. 3/4 of the ice, by volume, is gone. The surface area gives you a picture of how wide the ice is. The volume tells you how deep, how solid, how real it truly is. There is a number that researchers sometimes use to bring all of this into focus. At the current rate of change, the Arctic Ocean could see its first ice-free summer sometime between 2040 and 2060. Some models suggest it could happen even sooner. An ice-free Arctic summer would not mean the ocean has no ice at all. Scientists define it as less than 1 million square kilometers of ice remaining. threshold, a crossing point, unlike anything the Arctic has seen in at least 1,000,000 years. These numbers are not meant to frighten. They are meant to inform. Numbers are how the planet speaks in a language we can measure and record and understand. The universe runs on simple, elegant rules: cause and effect, input and output, action and response. The Arctic is showing us those rules in motion, written in miles of ice and degrees of temperature and decades of careful measurement. The satellites still look down each day. The measurements continue. The record grows longer, and in that long, patient record, the ocean is telling us something true about itself, about the land around it, about the air above it, and about the way all of these things move together, slowly and without pause, like the breathing of something very large and very old. Beneath the Arctic ocean floor, something ancient is stirring. The seabed here is not just rock and sediment. In many places, it holds enormous stores of methane, a gas that traps heat in the atmosphere far more powerfully than carbon dioxide does. This methane has been locked away for thousands of years, frozen inside a substance called methane hydrate. Methane hydrate looks almost like dirty ice. It forms when methane gas gets trapped inside a cage of frozen water molecules, held solid by the cold and the pressure of the deep sea. For most of human history, those cages stayed shut. The Arctic seafloor, especially in the shallow waters above the continental shelf, sits at temperatures just cold enough to keep the hydrates stable. But as the ocean warms, that stability begins to shift. Scientists have observed methane bubbling up from the seafloor in parts of the Arctic, rising through the water column and entering the atmosphere above. The amounts measured so far are still relatively small compared to global methane emissions from other sources. But researchers watch these sites very carefully because the potential stored beneath the seafloor is enormous. Some estimates suggest the Arctic seabed holds more carbon in frozen form than all the carbon currently in Earth's atmosphere. That number gives scientists reason to pay close attention. This is where the idea of a feedback loop becomes important. A feedback loop is when one change causes another change, which then makes the first change even stronger. Warming water releases methane. Methane warms the atmosphere further. A warmer atmosphere warms the ocean more. More methane releases. The cycle feeds itself. It does not need any outside push to keep going once it starts. Scientists sometimes call this kind of process a self-reinforcing loop, and the Arctic holds several of them working at once. The melting of sea ice is one. White ice reflects sunlight back into space. Dark open water absorbs it instead. So when ice melts, the ocean absorbs more heat, which melts more ice, which absorbs more heat. This particular loop already appears to be active. The Arctic is warming roughly 4 times faster than the global average, and the loss of reflective ice is one of the reasons why. Permafrost on the surrounding land adds another layer to this picture. Permafrost, that frozen ground that holds the memory of past ice ages, contains vast amounts of dead plant material that never fully decomposed. When permafrost thaws, that old organic matter begins to break down at last. Microbes consume it and release carbon dioxide and methane as they do. The land itself begins to exhale gases it has held in silence for tens of thousands of years. Scientists sometimes call the methane stored in Arctic permafrost and seafloor sediments a sleeping giant. The phrase captures something real. This is not a threat that announces itself loudly. It is quiet, gradual, and distributed across millions of square kilometers of frozen ground and cold seawater. It moves on timescales that are hard for human minds to feel in daily life. But the measurements show it is moving. What makes all of this so striking is how precise the conditions have to be for Earth to remain the way we know it. The planet sits at just the right distance from the sun to allow liquid water on its surface. The atmosphere holds just enough heat to keep temperatures in a range where life can function. The oceans circulate in patterns that spread warmth and cold across the globe in ways that stabilize regional climates. Each of these conditions depends on others. Pull one thread and others shift. The Arctic is one of those threads. It regulates temperature. It drives ocean circulation. It reflects sunlight. It stores carbon. It shapes weather patterns across the northern hemisphere. When the Arctic changes, the effects travel far beyond its shores. Winters in Europe, rainfall in Asia, storm tracks across North America. All of these feel the influence of what happens at the top of the world. There is something quietly astonishing about a system this large and this interconnected. The same ocean that shelters a narwhal beneath the ice also influences the monsoon rains that water crops on the other side of the planet. The same frozen ground that a polar bear walks across holds carbon that ancient forests stored before humans existed. Everything reaches everything else across distance and time, through chains of cause and effect so long and so slow that we are only now beginning to trace them fully. The sleeping giant has not yet woken, but the Arctic is listening to every degree of warmth the world sends its way, and it responds slowly, faithfully, the way all large and ancient things respond, with patience and with consequence. For centuries, explorers dreamed of a path through the Arctic. They imagined a shortcut, a sea route connecting the Atlantic Ocean to the Pacific, threading through the frozen islands of northern Canada. They called it the Northwest Passage, and for hundreds of years, it killed the people who went looking for it. The ice was the problem. The Arctic waters between Canada's northern islands were choked with thick, shifting sea ice. Ships would get trapped. Crews would starve. Some expeditions simply vanished. The most famous of these was the Franklin expedition of 1845. Sir John Franklin led 2 ships and 129 men into the Arctic. None of them came back. For more than a century and a half, the full story of what happened remained one of the coldest mysteries in exploration history. Scientists and historians pieced together clues slowly over generations. The wrecks of Franklin's 2 ships, the HMS Erebus and the HMS Terror, were only found in 2014 and 2016. The ice had held them for over 170 years. What the discovery of those ships revealed was remarkable. The wrecks were remarkably well preserved. The cold, dark water of the Arctic acts almost like a refrigerator for sunken ships. Wood that would rot survives for centuries in Arctic depths. Scientists are still studying the Erebus and Terror today, pulling careful details from the wreckage, trying to understand exactly what went wrong. The full story of those 129 men is still not completely known. The Arctic keeps its secrets slowly and on its own terms, but something has changed in recent decades. The sea ice that once made the Northwest Passage nearly impossible to cross is shrinking. In the summer of 2007, the passage opened almost completely for the first time in recorded history. Ships could sail through with little obstruction. What explorers once died trying to reach had become, at least seasonally, navigable. The route that connects the Pacific and Atlantic through the Arctic is now sometimes open for weeks at a time during summer months. This creates questions that scientists, governments, and shipping companies are all trying to answer at once. How reliable will the passage be from year to year? The Arctic ice does not shrink in a straight line. Some years, it retreats further than others. Some years, it returns more aggressively in winter. The passage might be open one summer and partially blocked the next, predicting exactly when and how the ice will behave is something researchers are still working hard to understand. The Arctic's ice is not a simple system. It responds to ocean temperatures, air temperatures, wind patterns, and ocean currents, all at the same time. There are also deeper questions about what lies beneath the Arctic waters that the melting ice is slowly revealing. The seafloor of the Arctic Ocean is still one of the least mapped places on Earth. Large sections of the ocean floor remain almost entirely unstudied. Scientists believe the Arctic seafloor may hold enormous reserves of oil, natural gas, and rare minerals. Several countries, including Russia, Canada, Norway, Denmark, and the United States, have overlapping claims to parts of the Arctic seabed. The legal and scientific questions about who owns what and what should be done with it are far from settled. Russia made a striking move in 2007. A Russian submarine descended to the seafloor beneath the North Pole and planted a titanium flag on the seabed. It was a symbolic gesture, not a legal claim, but it showed how serious earthly nations are beginning to think about the Arctic as a place of future importance. The race to understand and claim the Arctic is already underway, quietly, beneath the surface of the news. And beneath the surface of the ocean, there is still so much that science has not yet seen. New species are still being discovered in Arctic waters. New geological features are still being mapped. The deep trenches and ridges of the Arctic seafloor hold ecosystems that no human eye has ever observed. The cold and the darkness and the ice have protected those places for so long that they remain genuinely unknown. There is something wonderful about that. In an age when satellites can photograph every corner of the Earth's surface, when maps are precise down to the meter, the Arctic Ocean still holds rooms that no one has entered. It still holds questions that no one has answered. The mystery of the Northwest Passage was never really just about finding a trade route. It was about the human need to understand what lies beyond the next horizon. That need has not changed. Only the tools have gotten better, and the ice, slowly, is letting us closer. The deepest part of the Arctic Ocean sits in the Eurasian Basin, plunging to about 5,550 meters below the surface. That is more than 5.5 kilometers of cold, black, crushing water. No sunlight reaches that far. No warmth from the surface touches it. And yet, life is there. Scientists have found creatures living in the deepest Arctic trenches that seem to belong to another world. Tiny crustaceans called amphipods, which look a little like shrimp, swarm in enormous numbers, even at the greatest depths. They feed on whatever drifts down from above. The slow rain of dead organic matter that scientists call marine snow. This soft, pale drift of particles carries energy from the sunlit surface all the way to the pitch-black floor. The deep ocean is not empty. It is fed quietly and constantly from above. Some of the animals found in Arctic deep water are almost unimaginably old in their design. Sea cucumbers, which are soft-bodied animals that crawl along the seafloor eating sediment, have existed in forms very similar to their current shape for hundreds of millions of years. They survived the asteroid impact that ended the dinosaurs. They survived ridges and basins of the Arctic seafloor are still being mapped with any real precision. The Lomonosov Ridge, a long underwater mountain chain that stretches from Russia across to Greenland, rises nearly 3 kilometers from the ocean floor. It divides the Arctic Basin into 2 separate deep regions, like a wall running through the bottom of a bowl. Scientists believe this ridge was once part of the continental shelf before it broke away and drifted into the center of the ocean millions of years ago. The Arctic seafloor carries the memory of ancient geography in its very shape. Hydrothermal vents, which are cracks in the seafloor where superheated water rises from deep inside the earth, have been found in the Arctic Ocean too. The Gackle Ridge, one of the slowest spreading mid-ocean ridges on Earth, runs along the Arctic Basin floor and shows signs of volcanic activity. Where there is volcanic warmth and mineral-rich water, life tends to gather. Scientists expect that vent communities, with their strange tube worms and heat-loving microbes, exist along this ridge. Most of them have never been seen. The equipment needed to reach those places is expensive, difficult to operate, and still relatively rare. Now think forward. Not just decades, but millions of years. The Arctic Ocean will not always look the way it does today. The tectonic plates, those great slow-moving pieces of Earth's outer shell, are still shifting. Over millions of years, the continents will continue to drift. Some models suggest that in roughly 250 million years, the continents may converge again into a new supercontinent, the way they once formed Pangaea long ago. If that happens, the Arctic Ocean could shrink or close entirely, swallowed by the slow collision of land masses. The ocean that exists today is a temporary feature of a planet in constant motion. But before that distant future arrives, the Arctic will go through changes much closer in time. As the ice continues to thin and retreat, more light will reach the upper water. More photosynthesis will happen. More plankton will grow. The food web will shift. Species from the Atlantic and Pacific are already moving northward into Arctic waters as temperatures rise. Scientists have documented this migration. The Arctic Ocean is not just losing ice, it is gaining new neighbors. In the the very long view, the sun itself will change. About 5 billion years from now, the sun will expand into what astronomers call a red giant, growing large enough to swallow the inner planets. Long before that, its increasing warmth will have changed Earth's oceans beyond recognition. The Arctic, if it still exists in any form, will be unrecognizable. The water, the life, the ice, all of it will have transformed into something we cannot yet picture. But that is the nature of this planet. It has always been becoming something new. The Arctic Ocean that exists right now, with its drifting ice and its dark trenches and its ancient creatures, is just one chapter in a story that started billions of years ago and has no ending in sight. The deep trenches hold life that has never seen a human face. They hold geological features that have no names yet. They hold questions that the next generation of scientists will spend their lives trying to answer. The darkness down there is not empty. It is full of things waiting to be found. And above all of that darkness, above the drifting ice and the deep trenches and the ancient creatures moving through cold water, there is light. Not sunlight, something older, something stranger, something that has nothing to do with the sun's warmth and everything to do with the sun's power. The Aurora Borealis hangs above the Arctic Ocean on clear nights like a curtain made of color. Green mostly, but sometimes pink, sometimes violet, sometimes a deep and trembling red. It moves, it shifts, it folds and ripples like silk caught in a slow wind. People who have seen it for the first time often go quiet. There are no good words for it. The aurora begins 93 million miles away at the surface of the sun. The sun is not a calm, steady fire. It is a violent, churning ball of plasma, superheated gas that constantly throws particles out into space. This stream of particles is called the solar wind. It travels outward in every direction, a constant, invisible breath from our star, moving at roughly 1 million miles per hour. Earth has a shield. It is called the magnetosphere, and it is a vast magnetic field that wraps around our planet like an invisible shell. Most of the solar wind hits this shield and flows around us, the way water flows around a stone. But at the poles, the magnetic field lines curve lines of magnetic force down toward the top of the atmosphere. When those charged particles slam into the gases high in our atmosphere, the gases glow. Oxygen glows green and red. Nitrogen glows blue and purple. The altitude changes the color. Green auroras happen about 60 miles up. Red auroras happen higher, sometimes 200 miles above the surface. The whole display is essentially the atmosphere itself, lighting up from the inside, energized by particles that left the sun days earlier. The Arctic Ocean sits directly beneath one of the best aurora viewing zones on Earth. The oval-shaped region where auroras appear most often is called the auroral oval, and it rings the magnetic North Pole like a glowing crown. On strong nights, when the sun has released a large burst of particles called a coronal mass ejection, the aurora can spread far beyond its usual zone. It can be seen from Scotland, from Germany, from the northern United States, but above the Arctic Ocean, it is almost always there, given clear skies and a dark night. The light is silent. That is one of the things people find most striking. Something so large and so alive-looking makes no sound at all, though some people who have stood beneath strong auroras report hearing a faint hiss or crackle. Scientists are still studying whether this is real or imagined. The atmosphere at aurora height is too thin to carry sound waves down to the ground, and yet the reports persist. The Arctic keeps its secrets. What the aurora reminds us is that the Arctic Ocean is not isolated. It is not a remote, frozen place cut off from the rest of the universe. It is connected to the sun by a river of invisible particles. It is connected to Earth's magnetic core by lines of force that have existed for billions of years. The same magnetic field that guides a compass needle also guides those solar particles down toward the poles. The same sun that melts the sea ice in summer also paints the sky in winter. The atoms that make up that glowing oxygen and nitrogen were forged in the hearts of ancient stars long before our sun existed. When those submarine 60 miles above the Arctic Ocean is made of the same ancient stellar material as the bones in your hand. Everything in the universe is recycled. Everything is borrowed. The water in the Arctic Ocean was once part of a comet, or a cloud of gas, or the interior of a dying star. The iron in the Earth's core was forged in a supernova. The carbon in every living thing under the Arctic ice was assembled in the furnace of a star that no longer exists. The Aurora is a reminder of all of this. It is the sun reaching down to touch the edge of our world. It is the universe showing its work. It is the sky over the Arctic Ocean doing what this whole planet has always done. Quietly, beautifully, without asking to be watched. And so we come to rest here at the top of the world. The Arctic Ocean floats beneath a sky that has just shown us its oldest light. The ice stretches out in every direction, pale and silver under the moon. The water below it is dark and cold and full of life. Somewhere beneath the surface, a narwhal moves slowly through the black. A polar cod drifts past a curtain of ice crystals. A tiny copepod, no bigger than a grain of rice, carries enough stored energy to feed a chain of creatures, stretching all the way up to the bear on the ice above. This is what the Arctic Ocean is. Not just a body of water, not just a frozen place at the edge of a map. It is a living system, breathing in and out with the seasons, pulling heat from the tropics, and sending cold water south, regulating the temperature of a whole planet. Scientists call the Arctic a heat sink, which means it absorbs warmth that would otherwise build up in the lower latitudes. Without it, the climate systems that keep most of the world livable would shift in ways we are only beginning to understand. The ocean does this work quietly. It has been doing it for millions of years, long before any human eye looked north and wondered what lay beyond the ice. The Arctic was already at its task, cooling, circulating, keeping the balance. The sea ice itself reflects sunlight back into space. Scientists call this the albedo effect, which means the measure of how much light a surface bounces away. Bright white ice reflects up to 80% of the sunlight that hits it. Open dark water absorbs most of that same light as heat. This is why the loss of sea ice creates a feedback loop, where less ice means more heat absorbed, which means less ice the following year. The Arctic is sensitive in a way that no other ocean is. Small changes ripple outward into the whole system. But tonight, the ice is here. The moon is up. The ocean is resting. Somewhere far below the surface, the deep cold water that formed near Greenland is beginning its long, slow journey south along the ocean floor. It will travel for centuries before it rises again in some distant warm sea. The water moving through the Arctic Rite now may not see sunlight again until long after every person alive today is gone. That is the scale of this ocean's work. It operates on time that is hard to hold in the mind. And yet, it is happening right now beneath the ice in the dark. The Arctic has absorbed so much of our planet's history. Its sediments hold records of ancient climates. Its ice cores carry air bubbles from thousands of years ago. Tiny pockets of atmosphere preserved like messages from another time. Scientists read those bubbles and learn what the air was like before humans changed it. The Arctic remembers things we have forgotten. It keeps its records in ice and mud and stone. Indigenous peoples have kept their own records too, passed down through generations in language and story. And the deep knowledge of people who have lived beside this ocean for thousands of years. They understood the Arctic's rhythms long before any scientific instrument measured them. That knowledge is part of the ocean's story as much as any data point or satellite image. Everything we have talked about tonight connects to everything else. The plankton feeds the fish. The fish feeds the seal. The seal feeds the bear. The bear walks on ice that reflects heat into space. That reflected heat keeps the planet cool enough for forests to grow thousands of miles away. Those forests breathe out oxygen. That oxygen is carried by winds that circle the globe and eventually return to the Arctic, where they shape the polar vortex that keeps the cold air contained. The whole system turns together slowly, like a wheel that has been spinning since before any living thing existed to watch it. You are part of this system too. The water in your body has cycled through oceans and clouds and ice once beneath Arctic ice. Some of it may go back there someday. The planet is not a collection of separate things. It is one thing, moving together, holding itself in a balance so old and so intricate that we are still learning to read it. The Arctic Ocean rests at the top of the world tonight. The ice glows faintly under the stars. The water below it breathes. The planet turns. You can rest now too. Subscribe for a brand new Earth topic every night. One tap, and something wonderful is waiting for you tomorrow. Sweet